afternoon, everyone. My name is Bart. We'll be talking about offensive programming for the next 45 minutes. Before we start, I'd like to ask you to put all your devices in silent mode, both as a courtesy to everybody else, including me, and because we're recording sessions at this event, we don't want any embarrassing ringtones to show up in the video afterward. My head is very much in the way. So, defensive programming is more of a very broadly, not specifically defined technique to limit problems by just keeping things really simple, helpful failures, making robust code that only works one way, that cannot be used in another way, because we all know that long functions are difficult to debug. If there's a ton of if statements, it's hard to debug. The more something does, the more likely it is to fail. And if it is failing, the harder it is to fix it. So the way I describe it, especially within the scope of this presentation, is we're going to limit the complexity, so keep things simple. And if things do fail, make sure that the errors that you throw are helpful enough for anyone to fix the problem as soon as possible and as effectively as possible. So before we actually start with the content, I want to make one thing clear. Shit happens. Things go wrong, code breaks down, mistakes are made, we're all human. Fortunately, still we're all human. So the fact that we all make mistakes or that things go wrong in a project, even if it's a client project, is perfectly fine. It's natural, it is to be expected. What is important is how we deal with these problems. How do we respond when we realize that something did go wrong? How do we figure out what went wrong? How do we go about fixing the problem? And this is outside the scope of this current presentation, but something that also relates to this is how do you deal with this in a social perspective? How do you deal with your team members? It all revolves around how do we deal with failure. So this presentation mostly focuses around bugs or the prevention of it and fixing them. So things can go wrong mostly because of bugs. Most often, you wrote a piece of code that was supposed to do one thing, but occasionally does something that you didn't expect. Another very important thing, and this I see this very often in open source software, because there's a lot of communication between the authors, the developers, and the users of the code, is that the users do something with the software that the original authors, the developers, did not expect, did not plan for. And as a maintainer, there are two ways basically to respond to these things. When someone comes in your issue queue, for instance, or your issue tracker, and says like, I've been trying to do this, and it fails miserably. There are two ways you can respond. And one is, you're using my software completely the wrong way, closed won't fix. That's maybe makes sense, maybe that's perfectly within your right as a developer. It's not always the really nice way to respond. Most of the time it's like, all right, let's see what the problem is about. Maybe we can make the error message more useful in your case. Or maybe your use case is something we never thought about, but it's very useful and we should try and support it in the future. So show us how we can reproduce it, how we can make this an actual officially supported use case of our software project. So when people do these things with your software, if it's a client or if it's an open source software user, look at it from the bright side. It's a way to discover and fix new bugs because you basically expand your audience with tens or hundreds or thousands of other people testing your software to its limits instead of you having to do it all yourself. And the use case thing, like if you decide that when someone breaks your software with a new use case, you adopt that use case as officially supported because it actually, you didn't think of it, but it makes sense in the context of your project. It makes it more useful, which in turn also makes your software available to a wider target audience, and the whole circle repeats. So that's how you deal with failures, with errors. But the specific errors that you get, the specific failures, exceptions, how they are constructed impacts how people deal with them, how people will like or dislike your software. Because if an error is really, really obscure, there are probably a couple of PHP developers in the room here. If you, in PHP, at least that's what it used to be, if you forgot a semicolon at the end of a line, you get a nice syntax error from PHP that includes some word in Hebrew. in a way, it kind of makes sense because the original developers of the current Zen engine were from Israel. But to most people in this world, it's not the most useful error message you can get, and it's one of the top search queries for PHP errors in Google. Because it's useless. You don't know what it means, you have to look for it, you take the error message and error code, you look for it online, which means it's frustrating, it's stressful, and not being able to fix an error can result in a lot of different problems. You start yelling at each other in the office, it's their fault, instead of focusing on quickly fixing a problem. If it takes too long, you have to tell the client we're delayed from a few hours to a few days or a week. Nobody likes that. So the more predictable it is, and the easier it is that when something does go wrong to fix it, the more everybody likes their job. One of the main focuses, or maybe the main focus, is simplicity. The simpler it is, the less likely it is to break. And this is a very wide abstract concept. You can do it at anything. A function can take, if it takes less parameters, it is simpler. A function that only returns a value of one type and not of 3 potential types is simpler, therefore more reliable, easier to debug. Simpler code can be shorter functions. Simpler code can be less abstraction, sometimes more abstraction. It really depends on your particular situation. The important part is that you start thinking, how can we make the code in its current state as simple as possible, as easy to understand as possible? Because most of the time we spend reading code, our own code, someone else's code, the time that we spend actually writing code is much, much lower. So simplicity is not verbosity. I see that I've been experimenting with some of the styling of these slides. Verbosity is very often considered to be a bad thing, like long names are a bad thing. Not really. If you have a couple of things, a couple of variables that contain very similar values, the only way that you might distinguish them from each other is to have a slightly longer specific name that maybe exceeds the 20-character limit for your variable names. And that is fine, because the important part is that the code is readable and clean and simple. If that means some things are a little longer, so be it. We've had in the Drupal 8 lifecycle, like there's a lot of boilerplate code. Like we've got one class per file in PHP now, so there's a lot more code or comments that need to be written that aren't actually logical, so they can't really contain any bugs. But people felt they had to write more because a lot of people, when they started Drupal 8, they used very simple editors. Especially if you use an IDE that has auto-completion and automatic code inspection, verbosity becomes almost no problem at all because all those things that take long to type, your IDE does that for you. So simplicity in one way can be readability. Yeah? This is relatively hard to read compared to the next example because we have a statement here, an if statement with a condition, and another condition, and then a loop in it. So you've got 2 layers of nesting in a function which can also be already part of a class. So how can we make this easier? How can we make all these little things combined easier and do things step by step? It's a simple example, but we see that we split off the conditions to 1 per if statement, and we return early, which means that if this function is called and status is false, it will never reach this part. So if you know that status is false, and the function does something weird, then you know I only have to look at this condition. You don't have to dig through the rest of the function. You look at the small part that is relevant. We also reduce the nesting here, which makes it a little nicer to read. Also, nested blocks generally are harder to maintain. It's easier to add to them, and you get like 5 nested levels deep with loops and if statements. And it's really hard for a human being to read that and realize what the code is actually doing or what it is capable of doing. Most of the times it might be doing the right thing, but if you're trying to fix or find a bug, you're trying to find that one thing that doesn't go as expected, and then this is a lot easier to read than this. It's a lot easier to go through and be Sherlock Holmes and be like, this is what causes the problem. So readability and verbosity. Take your time, but this is more code, technically speaking. It's more lines of code. The logic is still the same. There are still 2 conditions and 1 loop. So it takes more code, slightly more typing, but all that extra work is not logical, so it can't really contain any bug. We already said it earlier, maintainable code is code that's easy to understand, easy to extend, easy to fix. So, especially if you work on something with multiple people, like consider the people in your team who might be more or less experienced than you are. If you cram a lot of code on the same line, it's like, I've got this very complex thing all down in 3 lines of code, that might be a really cool achievement for you. But your coworker, your teammate who needs to work on this piece of code next week will fucking hate you for it, because it takes them so much more time to read, and then they start working on it when they think they understand it. They end up not having understood those 3 lines of code of yours and spending more time on this particular code than should have been necessary in any universe. So think about this. Error handling is one of the most underestimated parts and the most hated parts of programming. Because we build something that works, right? A client requests something from us, a user of our modules, on Drupal.org, asks something like, hey, you built this, so we write it in such a way that it works. Very often we don't stop and think, okay, but what if it doesn't work? What if it breaks down? Then that's error handling. Both when your software, your code goes wrong, but also when you use other code and something goes wrong in there. How do you deal with that? Error handling consists of a couple of steps. The first step is, of course, finding out where the error came from. You can maybe get an exception for the stack trace, which describes the code execution, like line and file, exactly how it got to the line that caused the error. But is that the root cause? Maybe there was something else down below that was the original cause. Like if you have a caching error and the cache says, oh, exception can't save anything to the cache, then you might start looking in the caching class for what goes wrong there. Well, in fact, it was the database cache that internally uses the database connection. The database connection caused an exception. Not because the code there was wrong, but because the MySQL server was unavailable. Being able to find this very quickly and easily is part of good error handling. So if you write errors, think about that. Give people enough knowledge in your errors to find the original cause of the problem to make it really easy for them to fix. Include information like, oh, what's the environment and scope? So file and line numbers are really useful. What's also really useful is what are the values of the variables in that particular part of the code base. You can use a debugger for that. You shouldn't add that to an error message or an exception. And a stack trace is basically just how did the program get to the problem? Like from the start of executing the program, what happened to before the point where the problem was caused. If you throw an exception, we'll see how that works in the next few slides. This is done automatically in most programming languages. It's called a stack trace. So the next part is, okay, we found the problem. Now, what is the problem? What is it caused by? Like, why does this happen? So be very specific. Like, okay, this is what we tried to do this, but we couldn't because this thing went wrong. You can maybe explain why something went wrong. Maybe you can analyze in the code already the situation around you in the scope and offer suggestions for the developer, possible solutions, places for them to look at, maybe a link to documentation online, just to help them get started, to give them a feeling, to prevent them from being hopeless. Like if you find an area like, oh, I have no idea what this is about, that's horrible, that ruins your afternoon if you're unlucky. If you have a useful error message, it gives you hope. All right, cool, it was an error. And as a starting point, I can go to the handle page and I can find out more about this problem and maybe there's a fix there. A good error message or an exception and all this extra information around it is basically documentation for your error. This is an example from a little piece of code written in Elm, which is a functional language and is known for having ridiculously, amazingly, fantastically helpful errors. Look at this. This was a typo. The person writing this code wanted to type true. Didn't write true, wrote sure. So in PHP, you'd be like, true unfound, not found. End of story. Elm scans the code, finds another symbol, another constant in this case, called tur, and is like, or true, finds it defined elsewhere, and is like, that looks like each other. Maybe this is a typo. Maybe you meant that other thing. It's the information you need to get started, fixing the problem. So that was a part of a little bit about error handling. But detecting errors in your code is another step. One of the ways you can do that is validation. When you get parameters in a function, the first thing you might want to do is validate whether the parameters are correct. The email address is a string, but not every string is an email address. And you want to throw an exception if your values do not meet the conditions that you need to work under. So one of the things that you can validate is the input and output of systems. And a system can be any of these things. It can be a tiny little function to completely networked systems. Like, as long as it goes in a new system, it means it's input. If it goes out of the system, it's also output. If it goes from one network application to another, it's output and input. It's very important that you add validation to these points because the end, the public interface of your application is where other programmers work with. Your software's internals are mostly important to the people maintaining it. But if I write a module and some of you want to use it, you're not looking at the internal private functions of my module. You're looking at the API. You know, I tell you, oh, you need to work with these 5 functions. That's, as an outsider, if you want to use my library, that's the code that you work with. So if I tell you that, you start working with it, I need to make sure that those functions are very strict in validating what they take in, giving good error messages, because that's what you work with. The moment you start working on the internals, you'll learn more about how it works anyway. Ideally, you'd have good error messages there as well, but it's slightly less important. So this is my definition of input. Any data coming into the system or interaction with a system that originates from outside. So one class communicating with another class is input and output within the scope of that one class and the other class. One function called to another. In more generic terms, we can consider form input, web services. All those are input-output. If a web service gives me an XML response or a JSON response, it's their output, but it's my input. I can't trust that JSON response. I know that the documentation says that it's got this structure. But if some developer on the other side decides to update the response structure, the documentation note doesn't have to be updated, or I may not be notified. So how do I know if that structure is still valid? How can I trust that if I blindly work with that data, that my code won't break? I can't, so I validate it. Output is very simple, or very similar, really just the other way around. Usually, the best practice is like be liberal in what you accept. So if you get a value sent to you as input that is not entirely correct, but you can work with it, try to work with it. Be very strict about your output though. Make sure that your output is consistent, doesn't break in the future, because that makes your code reliable for others. However, if you don't want your code to break, it is the other way around. You want to be strict about your input, and you don't care too much about your output. It's really just interestingly how that works. One way of doing validation is using constraints. And there are many, many ways that you can do that. Using constraints is basically you have your constraints, your description of a particular data set, a format, how long a string can be. Even a regular expression can be a constraint. For instance, if you want to validate an IP address, you have a constraint that's probably about 50 lines long, because that's how complex regular expressions are. It's still a constraint, because what you do is you apply the constraint to your data, and you get a Boolean true or false, essentially, saying whether it's valid or not. You can have all kinds of error handling, but that's how a constraint works. If you work with static responses from web services in JSON or XML, you can write schema files. An XML schema is written in XML, like XSDs or RelaxMG. There's a JSON schema standard as well, also written in JSON. So you've got your constraints in a file. Generally, you apply it to the data, and you see whether it's valid or not. Another really simple way is whitelist and blacklist. If you've built forms in Drupal, if you use the select element, it has a hash options array, which is really just an enumeration of whitelist of allowed values. If someone submits a value for that element that's not in the options list, in the enumeration of values, validation fails. A blacklist works exactly the same way, but the other way around. A dynamic list can really just be an array, like match it against a set of computed values, see if it's in there. To go back to specific programming practices, type checking is one of the easiest ways of validating function input, in this case, that we have in programming languages. a language of JavaScript doesn't have this. PHP has it. We don't, in Drupal, use it everywhere just yet. And especially in this case, this is a PHP example. We type in on integers. So we basically say that the A and B variables must both be integers, and that the return value will also be an integer. This specific example is PHP 7. The return type is PHP 7, and typing on primitive values or scalars is also PHP 7. In PHP 5, you can type in on arrays and interfaces and classes, which is very, very good. This is just like one little extra step. And the reason this is really cool is because the language does your validation for you. If you call the add function with 2 strings, this will fail. The language will tell you that you passed on the wrong data. And if you've got experience with stricter languages like compiled language like Java, C, this is very important because these checks are done by the compiler of those languages. Because PHP and things like Python and Ruby are not compiled languages that we mostly use in web development. This is only done on runtime. We find it less important, but it's a really good way of documenting your code as well as having language level validation, which is much faster than anything else. So another way of making sure that you don't have to validate the same thing everywhere it goes. If you have an email address string that you want to pass on to a couple of different functions, you don't want every function to have to validate it again. So what you do, for instance, you can make like a value object, which is an object that doesn't do anything, it just contains values. It's basically a container for some raw data. Sometimes it may belong together. In this particular example, it just contains one single string, but it contains a single string for a particular format. So this is a Python example of a class that contains an email address. This is the constructor, which takes the email address string. As you can see, Python does not really do type anything. It has it in the latest version, but it doesn't enforce it. That's not in the example. And it tests in the constructor already. If it doesn't validate, throw an exception. And because you do this in the constructor, if the exception is thrown, that means the object never exists, that the object instantiation never completes, which as a consequence means you can never have an object that is invalid. Because if the data is invalid, the object prevents its own creation. You tell in every other function, Python doesn't have it in most versions yet, but in PHP definitely and other static languages, you can type in on the email address class. Yeah? So once you create the class, the object, you insert the email address string there, that's where the validation happens on the string. And then everywhere else you just type in, you just say, I want an instance of the email address class. And because we know that if an email address object exists, it is automatically valid, we don't have to do any more complicated validation. In our functions, we just type int on it, like we did here. So instead of int, we would have email address here, that's the name of the class, and the language would do every validation you need. This is a larger section. Exceptions are one of the most awesome error handling features we have. An exception is always a fatal error, but it's fatal only within a small piece of the code. Let's go back to the example of having a caching backend, which internally contains a database connection. If the MySQL server is unreachable, then the error is fatal for the database connection class, because it was supposed to connect to the server and it can't, so it can't do its job. So it runs into a fatal error. But for the caching layer, a missing database connection is not fatal. It's like, oh, then we don't cache, right? It's fine. We just pretend the calling code. If you want to set something in the cache, you don't really care if it's actually cached, because it might be a dummy cache, a null cache that pretends to cache something because you're in development, you're in a unit test. So it's fine. So it's fatal within the scope of the database connection, but not in the caching layer. And it bubbles up the call stack. So if the exception is thrown in the database connection class, and the database connection doesn't catch the exception, we'll see that in the next slide, it bubbles up to the calling code, which is the caching layer. And the caching layer is like, a database connection error. It's fine. Let it die out. It's fine. We'll take it from here. And that's what an exception does. Code can catch an exception to say, like, we can handle this. It's fine. So this is how you raise it or throw it. In Java, PHP, you throw a new exception. In Python and some other languages, you raise it. Creating exceptions in most languages are classes. These are actually built-in PHP exceptions, and the bat method call exception, like any class can, extends the bat function call exception, like the Unicode error extends the value error in Python. So if you want to handle any kind of value error, and you get a Unicode error, it's still a value error. So if you say as a code, I can handle value errors, sure. If it's a Unicode error, that means you can also handle it. So this is how you catch them. Any code that might throw an exception goes into a try block. So in the caching layer, the database cache, we would have a try block here that tries to query the database through the database connection object, which throws an exception. And then in catch, or in Python here in accept, you can catch specific exceptions. So if it's, in this example, even if a bad method call exception is thrown, it is a subclass of bad function exception. So it is a bad function call exception, which means if it is thrown here, this code will be executed. If you have a caching backend, it can be like, oh, it's a database error. This error stays blank, and then the code afterwards is resumed. So the moment you throw an exception, all code after that stops working, and it starts bubbling up to the nearest catch block that it can find in the calling function. If there's no catch block, it finds that calling function before that. If there's no catch block, it tries to find the function before that. All the way to the beginning of the call stack. In Drupal, that means it can reach index of PHP, because that's where we start executing. If you have an application that doesn't have a final catch statement all the way up there, it's called an uncaught exception, and the program terminates fatally, because if no code said that it could, remember that it was a fatal error, right? But if no other code says that it can handle the problem, that means there's nothing that can handle the problem, which means it's a fatal error in the scope of the entire application, so the application is exit. So PHP in our case, for instance, just says like, I stop executing, because there's no code that says it can handle this problem. We call it bubbling, basically, of data. It goes up the call stack, or up a hierarchy is bubbling. Fatal uncaught exception error, which terminates code execution. It doesn't mean that PHP crashes. It doesn't mean that Python or JavaScript crashes. It means that the code you wrote completely stops being run, being executed. And PHP, in this particular case, will exit just fine. It's like, PHP runs fine, because it's not a problem in the PHP code. It's nothing that breaks the PHP parsing. So, we already said that an exception should be caught when code can handle it. An exception indicates a problem if there's a piece of code that says, yes, I know how to deal with this problem, or in the case of the caching example, I don't care about this problem because it is not relevant, it is not a problem to me. Then you catch it. You can do a couple of different things. Catch what you can handle, so don't catch the generic exception class usually. This is a list of examples of what you can do when you catch an exception. Maybe you want to log the problem because it's something that needs to be inspected by a developer. In case of a database transaction containing like multiple actions on a database, usually you want to prepare them all together and then execute them all at once, so that when an exception occurs, you want to roll back the entire thing, because you don't want to leave your database in an invalid state when only 2 out of the 4 queries were executed. You can not do anything. You can just like let it die out, because for you it's not a problem. It is an expected problem. Like, oh yeah, the MySQL server is away a little bit. Oh, it's fine. We'll just log it and then not do anything else, so we don't let the exception go any further. We just pretend nothing happened. You can rethrow it. Like you can do a cleanup and a log, and then rethrow the same exception. Like, yeah, there's still a database connection, but in the meantime, I wanted to make sure that it was written to the logs. Any of these things. And what you choose depends on your situation, but really be aware, catch what you can handle. Don't pretend to handle any exceptions that your piece of code can't actually deal with. If it's still a problem for your code, even if it wants to do a cleanup or a log entry, if your code still thinks it's a problem, make sure the exception gets bubbled up again. This is really important. Don't let things die out quietly. So even if your exceptions and your errors are very helpful, if nobody sees them, they're not helpful at all. This is, in some situations, according to some people, this is related. Defensive programming is making robust code and everything. This are examples of non-robust code, but it's not really in the scope of this particular presentation. I wanted to mention it though, because these things are really important. They make your code much more robust. Like defensive programming is not necessarily just the things that I described, but these are very important things. Like you don't want someone to pretend they're someone else. You don't want someone to accidentally execute code through a database query or because you're running system commands on the command line through your code. Escape all the information you get. That's the input. Like if you see the XKCD comic about little bobby tables, if you get input from somewhere, make sure that it is valid also in the context in which you use it. If a function needs an email address with an @ sign, it can validate it to make sure that the string contains an email address. But if you use it in another context, the @ sign might have a special meaning. If you put it in on a command line, for instance, like certain characters have different meanings in different shells. If you forget to escape them, if you forget to sanitize and validate all that, it has a completely different effect, and it might break your code, or worst case, it might corrupt your data, or it might leak private information, and that's when you're going to have to face your legal team. So, in short, the benefits of defensive programming, of pausing, slowing down, thinking about your code, how do we make this as simple and readable and maintainable as possible, and if something goes wrong, how do we make sure that we can all fix it as fast as possible? It makes you a faster developer, eventually, because you don't have any unexpected delays where you have to spend half a day or 3 days fixing a tiny problem just because you didn't know where it came from. It will be less frustrating for you. People get grumpy when they're not happy, when they have to do something silly that they don't like fixing it. They get grumpy. If you get a whole team of grumpy people, you get fights. If you get delays, you have to face your client. The client has to face their stakeholders, all the way up to the CEO of their company, and you might get fired as a company because they want to go with someone else because you caused too many delays. So this predictability is really important for you, for your coworkers, and for your clients. Fail early. That's one of the things that type checking, for instance, does. The alternative to type checking is called duck typing, where it comes from the phrase, if it walks like a duck and talks like a duck or quacks like a duck, it probably is a duck. So you don't need to see the duck's identity card. You just observe it, and if you think, it acts like a duck, so it probably is. If you see an object, you don't necessarily need to see its identity, like of what type it is or what class it is, but you think, oh, it's got this one method. Oh, it's probably the object I'm looking for, so I'm going to call that method. That's an approach a lot of people take that I'm very much against, because that method might exist, but it might take different parameters, it might give you a different return value. Try finding the cause of the problem when that happens. So typing fails early, type checking. The moment it gets an incorrect data type, bam, your language tells you something went wrong. It's useful because it prevents you from completing a process. It allows you to fix the problem as soon as it happens, as soon as you introduce it in the code base. That's why testing regularly, locally, is really important. Fail often. There are several layers in your code where you have to have error handling and validation checking. So like where the public-facing part of your software that other people outside of your organization use definitely is a point where you have to do this. If you have a database error, make sure that the database error shows up in the database part of your code and doesn't move somewhere else, and doesn't let things fail elsewhere too much. Because then you see something falling over there, but the problem is here. So if you have many places where things can go wrong, that's good, because the symptoms are much closer to where the problem originated. Also, it keeps code portable. Yeah? So if you have your errors where they came from, that means you can take that whole section of the code and move it somewhere else, along with its error handling, because it's part of the code base. Hardened entry point is this public API thing. Make sure that the people who are new to your software don't get put off, even if they use your software the wrong way. Even if it's a coworker who's new to your programming language, who's new on the team, even if they use the code you wrote the wrong way, it might be their fault, but don't make it their misery. It makes other people's lives easier. It makes them like your code more. It makes them think that you're a better developer. It makes them want to use your code in their next project. The end of this wonderful presentation. I hope I've been able to make you think about this. We gave a couple of examples of the things that you can do, the topics that you can pay attention to in order to make your code much more robust, much nicer to work with. It is by no means an extensive list. There are many more things in the scope of defensive programming that you can look up. It is actually called defensive programming, so if you're interested in doing these things, just look up those two words online. There's plenty of books, plenty of other session recordings that you can look at. Thank you.